Continuing in 6.2.2, we already talked about 6.2.1 where we have 3 equations, 3 variables, and 3 solutions. And then we talked about how we can get no solution when we get something that's always false. And now I want to talk about when we get infinitely many solutions. So it looks like a straight line. So how do we define that? So again, this is just a little piece of your homework here. So we're looking at 19 and 21 right now. So my example here is number 20. So I'm going to start with step 1. I'm going to start by numbering the equations because that helps me keep straight what I'm doing. And then with step 1, we try to reduce that system of 3 to a system of 2 equations. And you can see each of these 3 equations is actually already in 2 variables, but I need to make sure that they're the same variable. So actually I can pick, step 1 is already done for us because 1 and 3 make up a system of 2 equations and 2 variables. Those both are defined in x and y. So step 1 is already done for us. Just have to identify it. So that's equation 1 and 3. And then in step 2, I try to solve that system. So in step 2, I'm going to use elimination. I think that lends itself nicely. The things will just eliminate. So I'm going to add 1 and 3 together. 1 is 2x minus y equals 1. 3 is negative 2x plus y equals negative 1. And when I add these together, the x's go away, the y's go away. I'm left with just 0 on the left and a 0 on the right. Well, this is always true. No matter what x and y are, this is always going to be true. Always true. Remember, if it's never true, we get no solution. If it's always true, that means we have infinitely many solutions. X and y could be any combination of things, and it will still be true. So, how do we define the solution? Because it's not any number at all for x, y, and z. There's infinitely many, but it's not just anywhere in space, right? It's actually a single line. So we're going to just define one variable and then give it a constant, and then we can define our other variables in terms of that. So I'm going to set, and it really doesn't matter what variable you pick. I'm going to pick x or y though, since those are the variables that gave me the always true statement. So I'm going to set y equal to some constant a, and then we'll define z and x in terms of that a. So we'll say let y equal a. Whoops, let y equal a. We're just defining it that way. And that way we can talk about how x and z are related to that. So if y equals a, then let's see, we have equation 1 says 2x minus y equals 1. So if I can replace y with a constant a, then I can solve for x in terms of a. So now I have a definition, a solution for x in terms of a, and I defined a solution for y in terms of a. So now I just need to find z, and with equation 2, I see I only have 2 variables there, so I'm going to rewrite equation 2. Oh, so this would be my step 3, finding that third variable by going back to the original equations. So I have x, I have y, now I need to find z. So equation 2, oops, sorry. That should be step 3 and equation 2. Equation 2 is negative x plus z equals negative 2. But I know x is 1 plus a over 2, so I'm going to do negative 1 plus a over 2 Actually, you know what I'm going to do? I'm going to solve in terms of just x first because that looks a little easier. So just moving that x to the other side, I get a positive x minus 2. Now I'm going to substitute my x and I get z equals 1 plus a over 2 minus 2, which equals, I want to combine these fractions to something a little prettier. So I'm going to rewrite the negative 2 as a 4 over 2. So I can combine the fractions, and then 1 minus 4 gives me a negative 3 plus a over 2. That's pretty good for a final answer. I'm going to take it one step further. When I have minus and then plus, I like to just switch the order and do a minus 3 over 2. So I'm going to make that my final z. It's the simplest form possible. And now I have a final solution. So I'm going to, oops. I'm going to test that solution. My solution is for x, I have 1 plus a over 2. For y, I have a. And for z, I have a minus 3 over 2. Your solution might look different if you chose to do x or y as your constant. I set y equal to constant, and I'm defining x, y, and z in terms of that. Okay, let's check that solution to equation 1, 2, and 3 above. So equation 1 is 2x minus y equals, let's see, 2x. So x is 1 plus a over 2 minus y, which is a. These 2's will cancel. I get 1 plus a minus a. A's cancel, and I get 1, which is my solution. Check. All right, checking my second equation. I have negative x plus z. Negative x is going to be negative 1 minus a over 2 plus z, which is a minus 3 over 2. I have a common denominator, so I can combine these, and I get, let's see, negative 1, negative 3 gives me a negative 4, and the a's go away. Negative a plus a. And then I have negative 4 over 2, which equals a negative 2, which is correct. And my last equation, equation 3, I have negative 2x plus y, which equals, let's see, negative 2x, that's negative 2 times 1 plus a over 2 plus y is a. So I get, my 2's cancel, but I still have the negative in front there, so I got to do negative 1 minus a over 2. Sorry, that 2 canceled. Just have that negative. And then plus a, which means negative a plus a cancels, and I have a negative 1, which is correct. So I've checked all 3 solutions are correct. So now I'm going to state my final answer is, actually it's right here, and I'll just highlight it right there.